Welcome back to the deep dive. You know, sometimes the biggest scientific leaps don't come from brand new, exotic materials. Sometimes the answer is sitting right there, maybe even on your desk. Today, we're looking at how something as common as pencil lead is actually being turned into, a high-performance, low-cost electron emitter. It's based on a really fascinating study in Nature Scientific Reports, our mission, to unpack how this everyday object becomes cutting-edge tech and, what that really means.
It really is amazing, isn't it? Finding a solution to something complex, expensive in pencil lead, it just goes to show breakthroughs can pop up anywhere.
Exactly. That unexpected element is what caught my eye, too. So let's set the stage. What was the big problem scientists were trying to solve before this pencil idea surfaced?
Well, researchers knew that carbon materials, things like graphene or carbon nanotubes, are great for electron sources. They're stable, handle heat, have the right shape, basically. But the real headache, the major hurdle, was getting them lined up properly. You need this controlled vertical alignment and sparse, too.
Okay, so getting them to stand up straight and not too crowded.
Exactly, and the ways they tried before. Often really expensive, fiddly work, like manually attaching tiny graphene flakes onto metal tips. It just wasn't practical for scaling up, a real bottleneck.
Right, and that's where the pencil comes in. This study talks about a much simpler way. Tell us about that.
Yeah, it's surprisingly straightforward. They use commercial pencil lead, specifically a 6B grade. They mention piloneox-eno as an example.
Just regular 6B pencil lead?
Pretty much. The key is how it's made. The manufacturing process, extrusion molding, naturally makes the tiny graphite flakes inside align themselves. Their flat sides, the bevel planes, tend to line up parallel to the length of the lead. Think of them like microscopic shingles, all pointing along the lead.
So the pencil lead already had the alignment they were struggling to create artificially.
Precisely. That's the elegant part. The structure was mostly there, they just needed to refine it. So what the researchers did was take this lead and graphitize it.
Graphitize? What does that involve?
Basically heating it up. Really hot, actually. Around 2,000 degrees Celsius for maybe 10 minutes. And they do this in an ultra-high vacuum. This heating process really enhances the structure. It creates these crucial vertically aligned graphene edges right at the tip where the lead is fractured. And those edges are perfect electron emitters.
Okay, so the heat treatment unlocks the potential that was already kind of hidden in the lead structure. But how did they prove this wasn't just a neat idea? How do they show it actually works?
Right, they needed solid proof. They used a few techniques. First, imaging with a field emission microscope and FEM. They saw these very distinctive patterns. They called them dragonfly patterns.
Dragonfly pattern.
Yeah, apparently that's the characteristic visual signature of electrons emitting specifically from graphene edges.
Yeah.
Seeing those patterns was strong visual confirmation. They also used other methods like raman spectroscopy, which analyzes the material structure using light, and STEM imaging for close-up surface views. It all pointed to those aligned edges being there.
So the dragonflies gave it away visually. What about performance? Did it actually emit electrons efficiently?
Oh, absolutely. It showed what's called low macroscopic field emission.
Oh, yeah.
Which basically means you get a good amount of electron current. They measured around 0.3 milliamps without needing a huge electric field. Just a few volts per micrometer. That tells you the emission from those graphene edges is really efficient.
Efficient is good, but what about reliability? Can it keep going? How does it hold up?
That's another strong point. It was remarkably stable. They ran it for 60 minutes, and the current barely dropped. The fluctuations were tiny, like 0.7% for lower currents, and still only around 9% even for much larger currents. That's really stable performance.
And what about the conditions? Does it need a perfect, expensive vacuum like other emitters?
That's a key advantage. Typical metal emitters are very sensitive, needing ultra-high vacuum. But this pencil lead emitter worked stably even at higher pressures, up to 10 to the -4 Pascal of nitrogen gas. That kind of robustness, being less fussy about the environment, is a huge deal for practical applications.
Okay, so it's efficient, stable, and less demanding. Did the electrons themselves tell them anything special?
They did, yeah. The energy spread, the spectrum of the electrons coming off, was different from metals. It was broader, about 0.7 electron volts, whereas something like tungsten is sharper, around 0.3 eV. And this broader spread matches theoretical predictions for electrons coming from graphene's pi bands. It's another fingerprint confirming it's really the graphene edges doing the work. Simulations back this up too.
Wow. So putting it all together, taking simple pencil lead, heating it just right, and ending up with a high-performance, stable, robust, and cheap electron emitter, That really is quite an aha moment. It makes you rethink where innovation comes from. It's not always about inventing something totally new.
Exactly. It's about seeing the potential in what's already there, understanding the fundamentals. And the impact here is potentially twofold. First, you have a practical, low-cost electron source. Think maybe cheaper, smaller electron microscopes or new types of displays, perhaps. But second, it also gives scientists a really easy way to prepare samples to study the fundamental physics of graphene edges themselves. It helps with both technology and basic science.
A win-win, like you said. It's a great reminder that sometimes the most advanced solutions are hidden in the most ordinary things. So maybe take a look around you. What other simple, everyday objects might be holding secrets, waiting for that spark of insight to unlock some amazing new potential? Something to think about.